In this video, we're going to look at Pythagoras' theorem. The video is split into three parts. Firstly, we will find the hypotenuse and look at Pythagorean triples. Then we will find the shorter side of a right-angled triangle. And finally, we will look at some problems in context. So firstly, you should already be aware of Pythagoras' theorem. It's only applicable to right-angled triangles. And we know that the longest side of a right-angled triangle occurs across from the right angle, so opposite the right angle. And we have a special name for the longest side, which is the hypotenuse. And Pythagoras' theorem states that the hypotenuse squared is equal to the sum of the squares of the other two sides, giving us h squared is equal to a squared plus b squared. Now there are many variations of this, so it might be a squared equals b squared plus c squared. Whatever variables are used, it's just most important to remember that the hypotenuse squared is the subject of the formula. So firstly, we need to identify the hypotenuse in right-angled triangles, and I've just told you that the hypotenuse happens across, opposite from the right angle. So in these triangles, it would be good for you to try and identify the hypotenuse. So at the moment, it would be good for you to pause the video and try these just now. Okay, welcome back. So hopefully you've got on okay with that. So in the red triangle, the first one, opposite the right angle is Z. So that is the hypotenuse. For the orange triangle, we have D. The purple is U. Yellow is the star. The light blue is A. Dark blue is G. And the green is B. So now we know how to identify the hypotenuse. We need to move on and have a look at an example on how to find the hypotenuse. So example 1, we've got a right angled triangle here and we have length 6, 7 and x, all in centimetres. So the first thing to observe is that this triangle is right angled, and that therefore allows us to use Pythagoras' theorem, which as we saw earlier is h squared equals a squared plus b squared. So the hypotenuse in this case is x. So x squared is equal to 6 squared plus 7 squared. And we can put the right hand side of this equation straight into our calculator, and we can then find that x squared is equal to 85. Now, I need x to be the subject of my formula, but just now I have x squared. So in order to undo this equation, if you like, the inverse of squaring something is square rooting it. So we need to square root both sides of the equation. So x is equal to square root of 85, which is 9.22. We're working in centimetres, and we've rounded that to 2 decimal places. Let's have a look at another example, or if you want to try this one, it would be a good idea for you to pause the video, go and try it, and then come back and see if you got the correct answer. So once again here, we know that we can use Pythagoras' theorem because we have a right angle. The hypotenuse opposite the right angle, in this case, is y. So y squared is equal to 1.2 squared plus 0.5 squared. If we put that into our calculator on the right hand side, we know that y squared is equal to 1.69. We need to square root both sides of the equation so that we get y by itself. So y is equal to 1.3, and we're working in metres. Now we're going to look at finding a shorter side now. So if we have a look at the first example here, we've got a right angle triangle once again. We've got lengths 39 and 89 and x, all in centimetres. Again, the drawings aren't to scale, so it's just a representation of what the triangle might look like. So we observe firstly that we've got a right angle triangle, and therefore we can use Pythagoras' theorem. Opposite our right angle is our hypotenuse, which in this case is 89 centimetres. So we know that the hypotenuse squared, which is 89 squared, is equal to the sum of the squares of the other two sides. So we've got x squared plus 39 squared. Now, we need x at the end of all of this to be the subject of our formula. So just now I need x squared to be the subject of my formula. But the x squared currently has a 39 squared being added to it. So we need to do the inverse of adding 39 squared and subtract that from both sides. We then have x squared being equal to 89 squared minus 39 squared, which gives us 6,400. And the same as before, the inverse of squaring something is square rooting it. So we need to square root both sides in order to get x. So here we know that x is 80 and we're working in centimetres. Let's have a look at another example, and if you want to try this one by yourself and then come back and check your answers, just now would be a good time to pause the video. So here we once again observe that we have a right angle triangle, and therefore we can use Pythagoras' theorem. Across from our right angle is our hypotenuse, which in this case is 2.9 metres. So that means that we've got 2.9 squared is equal to question mark squared plus 2 squared. Now we need the question mark to be the subject of our formula. So at the moment, the square of the question mark also has 2 squared being added on to it. So we need to subtract that 2 squared from both sides to give us question mark squared is equal to 2.9 squared minus 2 squared. And calculating the right hand side gives us 4.41. We need to square root both sides because that's the inverse of squaring something. And that will give us the required length, which is the question mark, and it's 2.1 metres. We're now going to look at some Pythagoras problems in context, where we don't know if we're finding the hypotenuse or finding one of the shorter sides. We need to examine each individual problem and decide what we're doing. So example 1. A ladder of length 4 metres is leaning against a wall. The top of the ladder reaches 2.5 metres up the wall. What is the distance between the wall and the bottom of the ladder? Now we can see here that we don't actually have a diagram. So firstly, it's good to have in your head what's going on, almost picture what's going on, and then put a diagram down. So you can see here we've got a ladder of length 4 metres. We've got our wall, which the top of the ladder reaches 2.5 metres up the wall. And then we've got the distance between the wall and the bottom of the ladder. And I've just called that D for short. Now, we need to assume as well that the wall and the ground meet each other at right angles. They are perpendicular because we wouldn't want to have a squinty building. So for that reason, we know we've got a right angled triangle, and we can use Pythagoras' theorem to work out any missing lengths that we might need to find. So I can see that opposite the right angle is 4 metres, and so that lets me substitute into my formula. So 4 squared is equal to d squared plus 2.5 squared. And I need to find d squared, but at the moment it's not the subject of my formula, so in order to make it the subject of my formula, I need to subtract 2.5 squared from both sides of the equation, giving me d squared being equal to 4 squared minus 2.5 squared. So d squared is equal to 9.75, and square rooting both sides means that d is equal to 3.12. We're working in metres, and I've rounded my answer to 2 decimal places, so I need to state that. Let's have a look at another example, quite a different example now. So the isosceles triangle shown has base of length 15 centimetres and perpendicular height of 9 centimetres. Find the perimeter of the triangle. So at the end of this question, I'm required to give the perimeter of the triangle. So remember, that is the total distance around the outside of a shape. Now I've got one of those lengths, 15, but I don't know what the other two lengths are, but I do know that those are the same as each other because it's an isosceles triangle. Now, if I split this triangle up, I can see that I've split my base in half here. Also that I've created 2 right angled triangles. So that will prove to be useful because it might mean that I can then use Pythagoras' theorem to work out any missing lengths. So if I redraw this, but just using the right angled triangle, I've got the question mark, which is the part that I need to find in the triangle. I know that the perpendicular height was 9 centimetres and the base was 15, but I've split that in half here. So the base of my right angled triangle then must be 15 over 2, which is 7.5 centimetres. So I've now got a right angled triangle. I've got one missing length, which allows me to use Pythagoras' theorem. So h squared equals a squared plus b squared. Opposite my right angle is my question mark, giving me the formula question mark squared equals 9 squared plus 7.5 squared. On the right hand side, calculating the 9 squared plus 7.5 squared gives me 137.25. Square rooting both sides to find out what the question mark is equal to gives me 11.72 centimetres. And I've rounded that to 2 decimal places, so it's good to state that as well. Now if I go back to my original diagram, I now know that these 2 question marks are 11.72 centimetres, And my perimeter then is equal to, remember that's the total distance around the outside of the shape. So that's 11.72 plus 15 plus 11.72. And altogether that gives me 38.44 centimetres.